So before we start, I did find the video. Unfortunately, I wanted just the video itself, but they turned it into a physics show. So here's a quick 2-minute video of the electric fence that we were just talking about and a little introduction to grounding.
Now, what happens when you touch an electric fence?
This clip made me laugh so much. It just goes to show we shouldn't mess with electricity.
So how do they achieve a simultaneous bipartisan electrocution?
The electric fence is quite simply a battery, and the battery, of course, has two terminals. One terminal is the wires that you see as the fence, and then what they do, they get these stakes and they put them in the ground, and that makes the ground the other terminal. So if you stand on the ground and touch the electric fence, you're completing the circuit, and hence you get a shock.
But why are Angus, Kent, and Carly not getting an electric shock right now? Well, Angus touches the electric fence. It's designed to keep animals in and deliver a brief shock.
Electricity will only flow if there's a path to ground. When those first initial few people touch the electric fence, they're standing on plastic chairs, so there's no path to ground.
Plastic
They're standing on
insulators.
which don't conduct electricity, and this prevents a circuit being formed between the grounds and the fence.
It's only when Joel takes off his shoes and holds the hand of the last person, then the circuit is complete and a huge pulse of electricity can flow through them all.
So why did they all jump at the same time?
The electric current is going to stimulate pain receptors, it's going to stimulate the nervous system, it's going to stimulate the muscles.
Don't try this at home.
It's going to be very painful. The reason these guys are more seriously injured is the fact that the electric fences deliver their electric charge in a high voltage, low current, short pulse. Now, if you compare this to mains electricity, that is high current and continuous. And the thing that causes damage during electrocutions is the amount of current that flows through them.
And please, don't try this at home. Electricity can be lethal.
No bueno. All right, so basically that kind of gives us the idea of grounding. The electrons need a place to travel to in order to travel through you and create a complete circuit. We're going to talk about that when we get into electricity specifically. But you have a perfect demonstration of grounding where your insulating stool, plastic or wood, would protect you even if you were touching an electric fence. The first few slides, we already talked about this. This lab we saw the other day, I mainly wanted to show you the concept of polarization. So notice how when you have insulators, the charges don't travel, but they polarize, meaning the electrons are going to move to the opposite side of your wall. The other concept that you want to know about in this lab is, we already talked about grounding, so I'm not going to go through this slide, and it's the same concept as the video, is that the electric shock doesn't happen until the electric charges are running through you completely and into the ground. So the ground is an endless reservoir of electrons, meaning that electrons can travel into an object and out of an object to make sure that everything is neutral, which is why we don't feel shocked every time we walk around or rub our feet on the floor or, rub fur continuously on, or balloons on our head. So the ground that we are standing on is going to add electrons or remove electrons to make things neutral at all times. Now, in the Electrophorus Lab, for those of you who didn't get the results, the correct results, because there were issues with some of the tape not charging correctly, we've got this Electrophorus video that will allow you to observe what actually is supposed to happen, but give it your best guess in terms of the answers to this pair deck. an electrophorus device. The meaning of that is a device that repeatedly generates static electricity by induction. Induction meaning you don't need the objects to touch, right? You continuously experienced that flash of light as you touched it near the styrofoam plate and you touched it above the styrofoam plate. It had to be alternating, and if you did it over and over and over and over again, you would always see that spark of light because it is a continuous infinite loop of charge transfer. So that's what an electrophorus is. The next thing we're going to talk about is the charges on the plate. But before we do that, I'm going to move on to this slide first. And I want you to just categorize. We talked about it earlier, but what type of, is it a conductor or an insulator in terms of the items we were using? The foam plate, the plastic handle, it was a foam cup, the metal pie plate, or the human hand. I want you to move those check marks around to identify what you think, and then we'll talk about it based on some of your results. Actually, where are the results? Here it is. Okay, good. Let's see what you came up with. Let me try to present this to you. Okay, so we've got there's some students that think the foam plate is a conductor. Foam is actually an insulator, and because it's made of the same material as the cup, which I made sure you held the item by the cup, it is also an insulator. The metal plate, because it's made of metal, is a conductor, and the hand was not as obvious. Well, actually, we did talk about skin, but more specifically, the hand allowed the electrons to travel through the light bulb, right? Or when you felt that shock. So the human hand is definitely a conductor as well. Moving on to the next slide, I want you to give me your best guess. I already told you that the styrofoam plate is negative. Before you do anything, what charge do you think the metal plate had before you touched it? And then after you touched it, you felt a shock or you saw that light flash. So what exactly happened when that light flashed? Show me how the electrons and protons are traveling. And I had a student do this in an easier method. You can use different colors. So I don't have red, but if you put red dots, that's your proton. And if you do, let me use blue. Blue dots for your electrons. Instead of drawing plus and minuses, it makes it a lot more efficient to just put red and blue dots. So what do you think? Remember, positive and negative charges doesn't necessarily mean that there's no electrons. It means positive means that there's more protons. Electrons mean that there are more negative charges. And then neutral means that positives and negatives are equal. So if you think it's neutral, make sure that you count the number of positives and the number of negatives to make sure that they're equal. If it's positive, you can just throw in a bunch of positives. If it's negative, you can just throw in a bunch of negatives.
Do for all three.
Do for all three. What's the metal plate before you do anything? What's the metal plate when you touch it and you see that electric shock, or you feel that electric shock? And then what happens after you remove your finger? What is the charge of the plate now? All right, so what happens is, before we do anything, we create a charge on our styrofoam plate, but the metal plate is neutral because we haven't done anything to the metal plate yet. So it always starts off with the same amount of protons as electrons. Now, when you hold that pi plate alongside a negative charge, you get something called polarization. So all the positives are attracted to the negatives, and all the negatives are trying to move as far away as possible. Now, when you're not touching it, there's nowhere for the negatives to go. All they can go, as far as they can go, is the very top of the plate. But when you touch it, the electrons can move further, right? They can move further away from this plate by going through your hand. That's what we call grounding. As a result, once all the electrons are gone, we end up with a positive pi plate. And hopefully that's the result that you got in your lab. If not, then you probably want to watch the video to make sure that you see this effect. You don't need to fill out the form for this one. I just walked you through that process. But I do want you to fill it out for this next one. Here, we've got a negatively charged plate. And remember, it was positive at the end of that first touch. So I'm giving you the answer. This should be positive. When you touch it, and this is when the plate is in the air, so it's not near that styrofoam plate. It's positive to start. When you touch it, what happens? And then what is the new charge of the plate once you remove your finger? All right, go ahead and put your answer. Red dots or blue dots, plus signs or minus signs. I told you it started as a positive charge. When you touch it, when it's above the pi plate in the air, it's going to want to become neutral. That's the state all objects want to become. So it's going to pull electrons into the plate, but just enough so that the electrons and protons are equal. So it's going to neutralize. No transfer between your insulating styrofoam plate. That stays negative. But in the end, you're going from a positive charge to a neutral charge. And then when you touch it, positive, neutral, positive, neutral. So this is a demonstration of the constant repetitive electrophorus effect of charging. We have conduction, which is when there's contact, your electrons transfer into an object. But you've got induction, where you can transfer electrons even without contact. And that's due to polarization. Okay? There's one homework tonight. It's a concept builder on conductors and inductors. And then if you didn't do the notes aren't due till after break, but I had some students get it out of the way early. Those are homework as well.